Can a single particle exist in multiple places at once? Not as a metaphor, but as a literal description of reality. In the early 1930s, quantum mechanics said it could. When Erwin Schrödinger followed that logic carefully, he realized the equations weren't just describing particles anymore, they were quietly redefining what it meant for something to exist at all. The real mystery wasn't whether a particle could occupy multiple positions, it was how does reality behave when its state depends entirely on observation. Quantum mechanics had shown that particles don't have fixed properties until measured. Electrons, atoms, even photons exist in superpositions, the mathematical mixture of all possible states. What Schrödinger highlighted was observation itself. The act of measuring the system forces it into a single outcome. Until that happens, reality remains undecided. To illustrate this, Schrödinger imagined a sealed box containing a radioactive atom, a detector, a vial of poison, and a living cat. The atom could decay or not. If it decays, the detector releases the poison, killing the cat. Until the box is opened, the atom and the cat exist in a superposition. Imagine spinning a coin frozen in mid-air, undecided, until someone catches it. And suddenly it clicks. The paradox isn't about cats, it's about information. Quantum mechanics describes what we can know, not what exists independently of interaction. This principle explains why quantum systems behave differently from classical ones. It also predicts how decoherence ensures we never observe macroscopic objects in mixed states. The environment constantly interacts, collapsing possibilities before we even notice. A single photon passing through a polarizing filter behaves exactly the same way. Until detected, it is both passing and blocked. Observation collapses its state. Schrödinger's thought experiment is simply a macro-scale illustration of this insight, which scales mathematically to real quantum technology. Observation defines reality. A system's state exists as a spectrum of possibilities until information is extracted, collapsing uncertainty into certainty. This principle underpins quantum computing, where qubits hold multiple states simultaneously. It powers quantum cryptography, where measurement disturbs the system. It informs precision measurements and atomic clocks. Schrödinger's insight wasn't just a paradox, it is a cornerstone of modern quantum technology. Reality doesn't always commit until we interact with it. Schrödinger's cat, the spinning coin, the undecided photon, they all remind us the universe is silent until we ask the right question. And when we do, everything snaps into focus.